All right. Okay. Right. Good afternoon. Sorry, good evening. Shall we start? Good evening. Shall we start? Am I audible and visible? Let me also check from my end. Good afternoon. Sorry, good evening. Shall we start? Okay. Fine. Right. Okay. I think the live is shared in the channels and groups, right? I think it is shared to channels and groups. And to download the question, you can either directly visit the Telegram channel, or else you can find the link for that in the pin message here in live chat, or else that is in the description of the video as well, right? If you go to any channels or the description of the video or the pin message here, right, from anywhere you can get the same, right? Okay, it's shared now. Yeah, right then. Okay, now listen. Good evening again. So we are in day 6 of our SQA discussions, right? Day 6 of our SQA discussions. We know we have been discussing about the past paper questions, starting from linear motion, projectile motion, then vectors, force equilibrium, right? So likewise, we discussed, and last week I discussed surface tension, right? And today also, I'll be doing this as a continuation of surface tension, because last week we discussed around 16 or 17 questions from surface tension, right? Around 16 or 17 questions. And today we'll be discussing our remaining questions on surface tension here, right? This is actually the day 6 of surface tension. And for 26 students, right? For 26 ones, you are now 24 weeks ahead of the exam, right? Now today is Friday, so exactly 24 weeks and 2 days ahead of the exam, right? So time flies, and it's our thing and it's your thing to make it useful and spend your time useful, right? In a useful manner actually, right? Okay, so 24 weeks. 24 weeks means that's not a considerable time period. That's a very small time period remaining now, right? Okay then. Then I hope you have downloaded all questions, right? Let's jump into the discussion, right? Let's jump into the discussion. Let me share my screen, right? Let me share the screen. Okay. Surface tension day 6. Right. Okay, you can see the screen, right? Can see, no? Right. Let's get into the discussion. Okay. 17. 17 means we have discussed for 16 questions last day, right? Now today we are in the 17th question, means we have discussed first 16 last day, right? First one, a soap bubble is gradually formed at one end of a glass tube by slowly blowing air from the other end. Starting from time t equals 0, which of the following graphs best represents the variation of excess pressure delta P inside bubble with time? Okay. See, now first get an idea how this is going to be formed. This is a rubber tube, right? It is given as a rubber tube. This is given as a glass tube. This is given as a glass tube, right? So the glass tube is something like this. Glass tube is something like this, right? And on one end, a soap bubble is going to be formed. Listen, on one end, a soap bubble is going to be formed, and this is how the soap bubble forms. No, let me use a different color to draw the soap bubble. Right now, it is like this. Listen, it is like this. Soap bubble is going to be formed starting from something like this with a small meniscus. Small meniscus means in terms of radius, because I'm interested about radius. What's the reason? Excess pressure is given by the equation this, no? See, excess pressure of a soap bubble or any meniscus is given by, right? Like a bubble layer again, yeah, from other end, a bubble, right? So that is given by 40 over R. That is given by 40 over R, where R is radius of meniscus. Where R is radius of meniscus, right? Radius of meniscus. So we are interested on that. Now, when the pressure from this side is increased, right? What we expect is this kind of a increase in curvature of the bubble, no? This kind of an increase of curvature of the bubble. Now, when that increase happens, what about the radius? That's the point here. Now, if you consider this kind of a bubble, see, the radius is something like this, and for this one, the respective circle is something like this. For this one, it's evenless. For this one, it is evenless. Which means, can you see that when this curvature increases, radius decreases, no? Right? When this curvature increases, now this is the behavior. Now from here to here, right? When it is pressurized, see, when pressure increases, what about curvature? Curvature increases, no? Curvature increases. When curvature increases, what about radius? Radius decreases. Radius decreases. Now my equation is this. When radius decreases, we know delta P increases according to the equation. Then for sure, I can say this is going to be an increasing trend. This is going to be an increasing trend, right? Increasing. It increases. Now, what are the increasing trends we have in the given graphs? Only 2 and 4. See, only 2 and 4. Now, my interest is on 2 and 4 now. And then, if we think a little bit further, right? If we think a little bit further, so at one point, once this excess pressure is not bearable by the pressure difference through the soap bubble explodes, no? Right? So at one point, down the line, this cannot be increased up to infinity or very large values, no? There's a limit. There is an end. That end is going to be the point where, right? This end is going to be the point where soap bubble cannot bear or cannot withstand for that excess pressure inside the bubble anymore. At that point, what happens is soap bubble is exploded. Soap bubble will be exploded. Then, at a particular point, after happening this, at some point, what happens is soap bubble will be exploded, right? Then, once the soap bubble is exploded, what happens is then pressure decreases again. Once the soap bubble is exploded, pressure decreases again. Now, in second one, there is no any decreasing part given. Decreasing part is given only in fourth one. Then this has to be 4. Has to be 4 because at one point, soap bubble exploded. Soap bubble exploded at one point. Soap bubble exploded at one point. Right? So likewise, using a few simple arguments, right? We were able to finalize the answer 4, right? Take down if anything. Take down if anything. So naturally, are given. Naturally, think of these scenarios given, right? So physics is anyway a natural subject, right? Always physics is based on natural phenomena, right? Natural phenomena and natural behaviors. That's a natural subject, right? All right, let's move on. This one is easy. The SI unit of surface tension is Nm minus 1. No? So if you don't know, use the equation and prove it. What is the general equation of surface tension? F equals TL, right? General equation of surface tension. Then if you need to find units of T, that is given by this. Plug these units. Force is measured in newtons. We need to find units of T, right? And L is measured in meters. What is L? Contact in length open to atmosphere, right? Surface tension contact in length open to atmosphere. Then units of T is Nm minus 1, right? Now in this particular question, dimensions are not asked. In any case, where the dimensions were asked, right? So you can find the dimensions as well. Dimensions of T, if needed, the dimensions of T, dimensions of force is mLT minus 2, and dimensions of T times L is L. Then these two cancels. Dimensions of surface tension is mt minus 2, right? Units are Nm minus 1, dimensions mt minus 2, right? Units are asked Nm minus 1, right? That's easy. That's easy, not a big deal. That's easy, right? That's easy, no? Right. Next. 19. See, a glass plate is dipped into a liquid dash shown in the figure. A glass plate, okay. If the glass plate makes an angle theta with the horizontal, the angle of contact between the liquid and the glass is, okay. The only thing you need to know for this particular question is the definition of angle of contact, right? When a move right? Just know the definition of angle of contact. Definition of angle of contact, right? What is angle of contact? Angle of contact. Angle of contact means angle measured between the tangent and the wall of the container through the liquid, right? Very important, that should be through the liquid. Angle measured between, this is the angle measured between the tangent drawn at contact point and wall of container, between and wall of container, right? Wall of container, or we can say surface. Most importantly, through the liquid, this is the most important part here, that is through the liquid, that is measured through the liquid, right? Through the liquid. Now, if this angle is given as theta, right? See, now if you draw a tangent here and if you measure the angle through the liquid, this should be the angle measured through the liquid, no? Isn't it? That's the angle measured through the liquid, right? Very simple as that. So we know this is an angle on a straight line, right? It sums up to 180. Then this has to be, see how easy that is? This is 180 minus theta. 180 minus theta. That is the angle of contact. So answer 4. Simple as that. 180 minus theta. Right? Knowing just the definition of angle of contact is enough. Knowing just the definition of angle of contact is enough. Can you explain 17th again? Question 17. 17. So about 17, initially it is starting from here, and when pressure increases, curvature increases like this. Curvature increases. When curvature increases, radius decreases. When radius decreases, excess pressure increases from the equation. Then it should be an increasing trend, and at some point bubble is going to explode. If the bubble is exploded, right, which means at some point it is going to decrease pressure, start decreasing pressure, bubble is going to explode, right? Then it should be an increasing and a decreasing trend. Only increasing and decreasing trend here is 4, no? So it should be 4, right? 19 is also done. 20. A cylindrical metal vessel of height 5 centimeters has a small circular hole of radius 0.2 millimeters at its bottom. Right, something like this. Now, in this one, there's a small hole like this at the bottom. There's a small hole at the bottom. Right. Now, if you don't get anything into your mind when you read the question, right? If you get something or not, just draw a sketch. Then you will see something. Draw a sketch. Right? बहुत करने पा, just draw the sketch. That's it. Radius 0.2 millimeters. Right. Radius 0.2 millimeters at its bottom. The vessel is lowered vertically into a liquid of density 800 with the bottom facing downwards. What is the minimum value of the surface tension the liquid must have so that the vessel can be lowered up to the brim without any liquid entering the vessel? All right. Now this is entered to a liquid up to the brim like this. Right. Now like this thing is entered into a liquid like this. Right. This thing is entered into a liquid like this, something like this. Right. Then minimum value of surface tension can be lowered up to the brim without any liquid entering the right. Okay. Now the point is this. Look at here. Point is this. Now when this liquid tries to enter through this hole, right? What happens is it creates a what? This is something we know. A liquid meniscus here. Like this. Let me draw like this. It creates a liquid meniscus here like this. That's a liquid meniscus. Right? If this liquid meniscus can withstand for this excess pressure, right? If it withstands for the excess pressure, which means no liquid is entered. But if this liquid meniscus is broken and if it doesn't withstand for the excess pressure, water comes in. Got the point? Now, otherwise, this should be able to be held by the meniscus itself. Meniscus is doing the thing, right? If meniscus is strong enough to balance this pressure difference, it will be kept as it is without entering liquid, right? Then what are the other lengths given? Height is given. 5 centimeters. No, then this height should be 5 centimeters, and this radius is given. Radius is 0.2 millimeters, and density of the liquid is given 800. Okay, then let's write the pressure difference. We know this is at atmospheric pressure P0, and this is also open, which means this side is also at atmospheric pressure, isn't it? That is also at atmospheric pressure. Then start writing pressure from some point. Let me start from here. P0 coming downward through the liquid plus H rho G, right? Plus H rho G. No, now we are here. And then from this liquid meniscus, you have to jump out, minus 2D over R. Once you jump out, again we add atmosphere. Once you jump out, again you add atmosphere. Then these two cancels, P0. Then it comes to H rho G equals 2D over R. Plug these values. H, 5 centimeters. Then 5 times 10 to the minus 2. Rho, 800. G equals 2T, we need T, over R. R is 0.2 millimeters, right? 0.2 millimeters means 2 times 10 to the minus 4 meters, no? 2 times 10 to the minus 4 meters, 0.2 millimeters. Milli means 10 to the minus 3, then 0.2 into 10 to the minus 3 can be written as 2 times 10 to the minus 4. 2 times 10 to the minus 4, right? Simplify. 10 to the minus 2 do, this 2 cancels. Then this 2 cancels. Right. Then simplify. 5 times 8, 40. 5 times 8, 40. 40. Right. And here 10 remains. Then 10 times 10 to the minus 4 means 10 to the power 3. 10 to the power 3 remains. Equals T. 40 times 10 to the power 3. Sorry, 10 to the power minus 3. 40 times 10 to the power minus 3. 40 times 10 to the power minus 3 means 0.04. 0.04 n minus 1. And minus 3, 1, 2, 3, 0.04. 0.04, answer 3. See, this is a kind of a different calculation, right? A little bit different calculation. Get this argument, right? If the liquid doesn't come into the container, which means this meniscus here, this is a meniscus, right? This meniscus here is holding this pressure difference. This meniscus here is holding the pressure difference, right? That's the thing. The meniscus here is holding the pressure difference. This meniscus here is holding the pressure difference. That's the point, right? Meniscus එක තමයි pressure difference එක බලාගෙන තියෙන්නේ. Meniscus is taking care of the pressure difference. Let's move on. Right, 21. When a glass capillary tube of internal diameter d is immersed vertically in water, the water rises inside the tube to a height h. Which of the following graphs best represents the variation of h with d? Right. When immersed in vertically in water, water rises inside, water rises, right? If a capillary tube is dipped in a liquid, we know, right, either that liquid should rise or it should depress. Rise is called capillary rise, and that depression is called capillary depression. Now, in this case, what we have is a capillary rise. We have proved this equation in the class, right? So, this is a capillary rise. Capillary rise, right? For capillary rise, we proved an equation. What is it? H rho g equals 2d over r. Equation of capillary rise. H rho g equals 2d over r. Now, diameter is given. Diameter is given instead. So, we know if diameter is given, right? Diameter is 2r, no? Then we can rearrange the equation like this to plot the graph. If we have to plot the graph, right, we have to take this equation to one of our standard shapes, right? We have discussed our graphing techniques we have, right? Last year we had the seminar, no? So we discussed the graphing techniques we have. So based on those techniques, only we can plot the graph. Otherwise, graphing is not something that we can just think of it and do. No, that's not the thing. Always try to approach mathematically, right? Do something mathematically and take it to a standard form, a standard shape of the curve, and then only we can think of the correct shape of the graph, right? Now, if we rearrange this, H rho g equals 2d over r. Instead of r, we can write d over 2. No? Then this becomes H rho g equals 40 over d. 40 over d. Right. Now identify our variables. Since h is our y variable, h is our y variable, d is our x variable, right? Then identify variables. First isolate h, and you better isolate our independent variable x as well. Then this is 40 over rho g, 1 over d, something like this, no? Then identify these variables. This is y, isn't it? And d is x. Then this is 1 over x. And whatever it is as a product with independent variable is called gradient. That is a gradient. Then at this point clearly you can see y is m1 over x. Y is m1 over x. That is an inverse relationship. So that is going to be an inverse curve. That is an inverse curve, right? Any inverse curve has this shape. Any inverse curve's shape is this, the inverse shape. That is called the inverse shape. So answer 1. So likewise, mathematically, we have to do something. Mathematically, this is not something that you can think of and do. Do something mathematically. Like this, do something mathematically. Right? We have to rearrange the equation in such a way that we can reach our final goal, final target. Right? Target right. 22. As shown in the figure, now in this particular question, mistakenly figure is not printed. Right? I will give you the figure. This is how this figure should be. This is how this figure should be. Right? That's a typing error. This is how this figure is. Right. This is how the figure is, and the nylon is like this. This is how the figure is, right? So please take note because it was not printed because of a typing error, typing mistake. Right. 22. As shown in the figure, the spaces between the nylon fibers of a nylon umbrella cloth can be approximately considered as a circular, if the diameter of each space is L, right? Diameter is L, which means this is L. Diameter is L. And the density of water is D. Density of water is D, right? The minimum surface tension required to prevent water from seeping through the spaces is, right? This is a different question, a little bit different question. Take the angle of contact between water and nylon has to be 0, right? Now, our idea is this, right? Our idea is this. If you take a side elevation, this is how this is visible from a side. Now, nylon cloth is like this, and this is how this liquid drop is. This is how the liquid drop is, right? This is how the liquid drop is, and all around the liquid drop, we know these are the contacting points, right? In all these contacting points, there will be forces due to surface tension, and mg is counterbalanced by this force due to surface tension. Mg is counterbalanced by this force due to surface tension if this liquid doesn't seep, right? Doesn't seep down or seep through, right? That's the point. And one more important thing, and a very important thing, this liquid drop is in contact with atmosphere from both sides. See, from this side also it is in contact with atmosphere, and from this side also it is in contact with atmosphere, which means all surface tension forces are duplicated. Wherever there is a contact with atmosphere, there are surface tension forces, no? Then there are two surfaces for the same object which are in contact with atmosphere. Then all these surface tension forces should be duplicated, doubled. They are doubled. Then without marking T, you have to mark these surface tension forces as 2T. Now it is not T, that is 2T because of these two surfaces, right? So instead of T, you have to use 2T, a special case. So usually we have T and 2T cases in soap materials, right? In soap, but here this is not soap, but still, this happens because this liquid drop is in contact from both sides with atmosphere, right? Okay, then find the equilibrium. See, F equals, considering vertical equilibrium, right? F equals mg. We know F is TL usually, but now it is not T. It should be 2T. 2T into contacting length equals mg, right? So what about surface tension? Minimum surface tension required. Okay, we asked about surface tension. 2T into L. Contacting length. Contacting length is all around this. This one, no? Then radius of this is L over 2, no? Radius is L over 2. Contacting length is 2 phi r. Then 2 phi r is L over 2. M. We know M can be written as V rho. Volume into density. Volume of a sphere. Now this is a spherical shape. Volume of a sphere is 4 over 3 phi r cube. R is L over 2, then L over 2 whole thing cube. Rho is given as D, G. Like this. Simplify. Then phi to phi cancels. Right? Phi to phi cancels. This 2 to this 2 also cancels. Right? Okay. See what's remaining. Here 2T times L. From this side, may 2 cancel. Let's cancel this 2 as well. See, this 2 also cancels. No? This 2 with this 4, it is 2 again. Right. Now, see what is remaining from this side, only TL remains. TL. And here 2 over 3 remains. And this is L cube over 2 cube means 8. DG. Right. Then 1L2. 1L also cancels, only square remains. 1L to 1L cancels. Subject T and this 2, this cancels 4. Subject T. Then L squared dg over 3 into 4, 12. L squared dg over 12. Answer 4. Right, these are different question, and a good question came. This was in 2011. 11. That's a good question with a little bit different idea. Right? Write it down. And using this T 2D instead of T is very important and critical. Right? Using T instead of 2D is very important and critical. The reason is it is in contact with both sides with the respective atmosphere or air medium. Right. Next. 23. A thin layer of water exists between the bottom of cylindrical bottle and a glass plate, as shown in the figure. Right, now this has to be the glass plate. This one has to be the glass plate. Right. The radius of bottom of the bottle is R, that is marked. When the bottle is slowly lifted, at a certain instant, the angle of contact between the water and the bottom of the bottle becomes theta. See figure. Right. At that instant, the magnitude of the forces acting on the bottom of the bottle, due to surface tension, T of water is, right, due to surface tension, T of water is, right, angle of contact is given. Right. Then we know along this particular direction, surface tension acts, right? Then this vertical component is going to be T sine theta, right? And this component is going to be T cos theta. But same T cos theta acts all around this bottom, no? Same T cos theta, this one. Same T cos theta acts all around the bottom in all 360 directions. All around the bottom in all 360 directions. Then all the horizontal forces are going to cancel. That's a point you should understand. All horizontal components cancel each other. Then only vertical components remain, right? So that is with T sine theta, no? Then let's write F equals TL, considering that, right? General equation of surface tension, F equals TL. T is T, contact in length. Sorry, T is not T, T is T sine theta. Contact in length is all around this bottom. That is 2 phi r. Nothing cancels. Then 2 phi r t sine theta. First answer. Okay. Now, if you deal with this given angle of contact the right way, there's nothing to do in the question. Right? Just apply F equals TL, that's it. Right? Nothing much to do. 24. A small amount of powdered pepper is sprinkled onto a surface of water in a cup. The water surface is first touched with a clean, dry fingertip. And fingertip is then rubbed with a small amount of soap. And then the same process is repeated. Which of the following observations is most likely to be made? Right. So just know that if there's dirt or soap, right? Right? Pepper particles or pepper powder is repelled using those. That is repelled. Keep that in mind. That is repelled because of the adhesive force, right? Because of the adhesive force due to dust or dirt and soap, pepper is repelled. Right? These are small experiment. Experiment means a demonstration we do usually, right? Now you also can try this out at home, right? Get a small amount of pepper, right? Pepper powder. pepper powder, and put it into a small cup or something, and you can clean your hands and put it into the cup and see what's happening with pepper, and then rub your finger on soap and repeat it. Then you will see it is repelled, right? So from that knowledge only we can argue this. From that knowledge only you can argue this. Then if there is a clean one, no change, it should be no change. Then in 3 and 4, no change answers are there. And soapy finger rip, when there is soap, it should be repelled. Then particles gather around, not gathering around, move away, because that is repelled. No, that is repelled. So answer 4, right? Because of dirt, dust, soap, right? These ones, pepper powder is repelled. Pepper powder is repelled, right? So that's a small demonstration we do, right? 25. 3 spherical liquid films. Films means bubbles. Films with surface tensions T1, T2, and T3, right? Then their surface tensions are T1, T2, and T3. No, are in equilibrium as shown in the figure. Their corresponding radii are R1 equals R, R2 equals 2R, R2R, and 3R. Which of the following relationships between the surface tensions is correct? Okay. So we know, right? This is a simple one. We know all of them are in atmosphere. Then atmospheric pressure acts outside these films. Atmospheric pressure acts outside these films, outside the films, right? Now let's assume pressure inside as P. If there is P, we know pressure at any point of same air medium is same. Pressure at any point of same air medium is same. Then if this is P, this is the same air medium. This should also be P, right? This is also the same air medium. This should also be P, because this air medium is the same, connected from inside. See, this is the same air medium, like this. So that is connected. Then what is the observation? Pressure difference through these all menisci are same. Pressure differences through these all menisci are same, right? Always we know pressure inside the meniscus is greater. Pressure inside the liquid meniscus is always greater than pressure outside the meniscus. Now, in each meniscus, pressure difference is P minus P naught. No? In each meniscus, pressure difference is P minus P naught. Right? That is same. Right? Pressure differences are same. This is the most important observation here. Pressure differences are same now. Pressure differences are same. If pressure differences are same, right, we can argue this way, no? Then delta P1 equals delta P2 equals delta P3, isn't it? Pressure difference through a liquid meniscus, right? Now these films means should be probably soap, right? It is written as 40 over R. Then delta P1 can be written as 41 over R1. Delta P2 can be written as 42 over R2, and 3 43 over R3, right? Now 4 cancels, right? And for R1, R2, R3 values are given, plug those. T1 over R equals T2 over 2R equals T3 over 3R, right? R also cancels. R2, R cancels, right? See what's remaining, right? See what's remaining. That's it. So what's remaining is T1 equals T2 over 2 equals T3 over 3. T1 equals T2 over 2, T3 over 3. Answer 5. Right? 5. Right? So most important observation and your approach should be, you have to see these three as 3 equal pressures, 3 equal pressure differences, right? 3 equal pressure differences. That's a point in the question. That's a point. Right? Let's move on. 26. Due to the surface tension of water 0.07 N-1, certain small insects are able to walk on the water surface of water by depressing the water surface. Right? The feet of the insect may be considered approximately spherical, as shown in the figure. When the insect is stationary, the position of one leg is shown. The radius of circular cross-section of the spherical foot at the water surface is r equals 2.5 10 to the power minus 5 meters. The mass of the insect is, right, mass of the insect is given. The weight of the insect is supported equally, right? The weight of the insect is supported equally by its 6 legs, right? There are 6 legs and it is supported equally. The approximate value of cos theta, see figure, take 5 equals 3. Okay, right. Now, because of this angle of contact, we know, right? We know surface tensions are going to act this way now, as we did in the previous one. Then vertical component is going to be t cos theta, right? That is t cos theta. Then likewise, there are infinite number of components of t cos theta, infinite number of t cos theta, right? T cos theta acts. Then with that, it is going to counterbalance. See, with that, it is going to counterbalance. Then, if you think of the whole insect, say force on one foot is F. Let's assume force on one foot as F. Then vertical equilibrium, due to vertical equilibrium, by using 6 legs, then 6F, mg is balanced, isn't it? By using 6 legs, mg is balanced. We know F is TL. F can be written as TL. Then 6 times TL equals mg, right? 6 times T. T was given 0.07. Right, let me write it as 7 times 10 to the minus 2. L, contact in length is 25R, around this, right? Around this, no? 25R. Then 2, 5 is 3, R was given 2.5 10 to the minus 5 equals mg. M was given, right? M was given. Oh, wait, I have missed cos theta. Then with this t, there should be a cos theta. With this t, there should be a cos theta, no? Right. Here. With this, there should be a cos theta because this is not t. This is t cos theta. Right? This is not t. This is t cos theta. Right? Now here also, this is not t, but that is t cos theta. That is t cos theta. T cos theta L. T cos theta L. Because this component is t cos theta, vertical component is t cos theta. Right? T cos theta L. Okay, and mg. mg 5 times 10 to the power minus 6, g 10. Simplify this. 10 to the power minus 6 into 10 is 10 to the power minus 5, no? Then for these two, this 10 to the power minus 5 cancels. Right? Then what else? What else is going to cancel? Then let's subject cos theta. Let's subject cos theta. 5 these two cancels. See? 2 times 2.5 is 5. This 5 cancels off with this. Right. Subject cos theta then. Cos theta equals, when this 10 to the power minus 2 goes to the other side, it becomes 100. Right? And here, what are the numbers remaining now? 6 times 7, 42. 42 times 3. 42 times 3. Right? I have to simplify this. By 2 this cancels, then 50 over 21 times 3. Then the ratio is 50 over 63. This we have to find. 50 over 63. What's the ratio? 50 over 63. 50 over 63. Right? It comes to 0.79. This is 0.79. This is 0.79. This is 0.79. 0.79. So 0.8 is given. Right? It's asked about the approximate value. Right? 0.8 is given. Right? about a insect, this kind of force equilibrium of an insect. I think last day also I discussed one question, right, from equilibrium. Last day also we discussed. Can you explain 25 again? 25. 1 second. 25. In 25, there's nothing. Just see that, just identify that pressure differences are equal. Pressure differences are equal, right? All are open to atmosphere from one side of the surface, and inside this a common air interface or common air medium for all of them. Then pressure differences are same, right? Common air medium, I assume that as P minus pressure at the atmosphere P naught, then P minus P naught across all the bubbles here, right? Only this part is a bubble from here to here. Only this part is a bubble, right? Only this part is a bubble. So across all bubbles, that's the same pressure difference. Then you can equate their pressure differences, delta P, right? 27. Right. All good so far? Others? Others? Are all good so far? Now, how many questions we have discussed? 26. 26 means around like 10 questions we have discussed. Any questions? Or is it all good so far up to this point? Okay. It seems it's clear. Right. Let's move on that. 27. Which of the following phenomena is not a consequence of surface tension? Right. Formation of spherical water droplets. Yes, exactly due to surface tension. We discussed. Right. Rise of water in capillary tubes. Yes, capillary rise. Capillary rise. Ability of insects to walk on the surface of water without thinking. Yes. Right. The question just, I mean, immediate previous question also was that excess pressure inside the soap bubble. Yeah. Delta P equals 40 OR. Right. All good. Okay. Nice. Escaping of water molecules from surface of water. No. Right. What is that? Escaping of water molecules from surface of water. That is called evaporation. That is due to evaporation. That is due to evaporation. That is due to evaporation, not surface tension. That is evaporation. Right. So answer 5. That is 5. Right. Statements. 28. The figures show 5 different clusters of soap bubbles in air, drawn by a student. If the centers of all bubbles in each cluster lie in the same plane, which of the following clusters represents a physically possible and a correct shape? Right. So if you need to check about the possibility of this type of a question, right, what you can do is you can check the pressure difference, right? Something like this. Now we know, listen, we know if this is a soap bubble, see, if this is a soap bubble, right, we know pressure inside the soap bubble is always greater than pressure outside the soap bubble, no? Right? Now, that's why P1 minus P2 becomes 2TOR. That's why P1 minus P2 becomes 2TOR. Then, always when you consider meniscus, right? Always when you consider meniscus, pressure inside meniscus should be greater than pressure outside the meniscus. Pressure inside meniscus should be greater than pressure outside the meniscus, right? To counterbalance that pressure difference, there's a pressure difference anyway. Otherwise, there's no curvature at all. If there's no pressure difference, there's no curvature, right? To counterbalance that pressure difference, this meniscus forms, right? Now, in a question like first one, right, there cannot be flat surfaces. Cannot be flat surfaces because if there's a pressure difference, there's a radius. Delta V equals, delta V equals 2TOR, no? Right? Then there cannot be any flat surfaces. So 1 is wrong. Right? Now, if you check the second one, we know when radius decreases, what about pressure difference? Pressure increases. When radius decreases, pressure increases, which means higher pressure from these two is inside this, no? Higher pressure is here, and this is a lower pressure, comparatively lower pressure. Higher pressure is at this side, P1. right? Always this curvature is always it's towards the higher pressure. Now, as an example, if you have this kind of a meniscus, right, this has to be the higher pressure, this has to be the lower pressure, right? Now, if you have this kind of a meniscus, this has to be the higher pressure, this should be the lower pressure. Always, when this is pressurized from this side only, this curvature comes, right? Again, it always curve to the towards the higher pressure, Now, higher pressure is this side, then this curvature should not be like this, it should be like this, should be opposite. So 2 is also wrong, right? It should be opposite curvature. To balance the higher pressure, right? Okay, in third one, these two are higher pressures. These comparatively lower pressure. This curvature is different and that is to the same side. That is kind of okay. Let's check the others as well, right? So this kind of okay for now. In third one, there is no different meniscus here. See, there's no different meniscus here. When may part take a different it should be different when pressure differences are different, right? Because pressure difference between this meniscus is, say this pressure inside this P1 and pressure inside here is P2, then pressure difference across this meniscus. I hope this writing is clear. Pressure difference across this meniscus is P1 minus P0. But pressure difference across this meniscus is P1 minus P2. When pressure differences are different, radii should be different. When pressure differences are different, radii should be different. Right? Now here no different radii are drawn, wrong. Right? In fifth one, again you can check this. This is the highest pressure. Right? This is second lowest pressure. Then this should be curved towards the higher pressure. Right? Not the radius as same as this, but the curvature should be to this side like this. Should be curved towards the higher pressure. Wrong. Then answer is 3. Right? Now, if you write an equation for pressure also, you can get an idea. But since this is a MCQ, I don't recommend you to write 5 equations considering all 5 scenarios. Right? So likewise, just by looking at this, you can argue. You should be able to argue like this. Right? Always this pressure is higher. That's why curvature comes to this direction. Right? Take it out. Right? So argue naturally like that. 29. A long capillary tube of uniform internal radius is dipped vertically into a beaker containing water of density dW. The water rises in the capillary tube to a height h0 as shown in the figure. And oil of density d0 is less than dW, is then slowly poured onto the surface of water without disturbing it as shown in figure, right? You can clearly see, right? Oil surface is here without disturbing water surface like this. Oil surface is here. Assume that water and oil are immiscible. Which of the following graphs best represent the variation of the height h of the water column inside the capillary tube? Right. Now this is not just a normal capillary rise because there are two liquids. In such a scenario where it is different from what we have proved, right? Start from one end and start writing pressures. Right. Let's start from here. This is open to atmosphere. Then this should be P0. And this is also open to atmosphere. This should be P0. Right? So start from this and let's write down pressures. P0, starting from P0. Right? So here we have a meniscus. Jumping out of the meniscus. Minus 2D over R. Then you can come down through this tube up to this point, through the tube. That is plus H rho G. Now we are here. Now we are here. Now you have to go up again. Through the liquid. What we call oil, right? Through oil. Then minus H dW. Sorry, HD. Let me write it properly. Then dW and dO. Then this should be water. Water means dW. This is dOg. and again we are back at the atmosphere, right? Started from this point, starting from that point, right? Starting from that point, come downwards, right? Come downwards, and you can cross the meniscus, come down again through the liquid, right? Plus H rho G, and go upwards, minus H rho G through a liquid, and we are back at the atmosphere, right? Then at that point, these P naught cancels, right? Now, in these graphs, we know H is acting as y-axis and simple H is acting as x-axis. Then isolate those terms and try to take it to a standard shape. Isolate terms and take it to a standard shape, right? Then if this is subjected HDWG, right? Take it to the other side. Then HDOG plus 2TOR, no? Subject capital H, right? Then capital H equals, you can divide the entire equation by dWg, right? You can divide the entire equation by dWg. Then this is dO over dW. G cancels, no? H remains. dO over dW, H remains. Plus here 2T over R dWg. Right. Now it's done. Identify these variables. This is our x variable. Whatever it is as a product with x is gradient m, and this is y, right? And this whole term is intercept c, right? Clear? Right. Then what's the shape? Y equals mx plus c. Only y equals mx plus c curve here is this. So it's 4. Right? See, that's a creative question, 2018. Creative question from capillary rise, we know. Right? Capillary rise. You can't just think and get a graph, right? Mathematically approach the graph, right? You can mathematically approach the graph, right? Approach it mathematically. Approach it mathematically. Right, okay, let's move on. 30. The capillary tube is dipped vertically into a container of water having a large cross-sectional area, as shown in the figure. The system is placed inside an elevator, and elevator initially at rest. Right. The open end of the capillary tube is 40 millimeters above the water level in container, and the capillary rise is 8 millimeters. If the elevator is moving downwards with an acceleration of 5 and in free fall, what will be the corresponding capillary rise? Okay, 2020. So we know general equation of capillary rise is H rho G equals 2TOR, no? H rho G equals 2TOR. H rho G equals 2TOR. Then when that is at rest, it says 8, ne? And the capillary rise is 8 millimeters. Yeah, initially it is 8 millimeters. Then initially we know this is 8 rho G equals 2T over R, right? So this is something we have satisfied initially. And about this G, since this G is coming from H rho G, right? Pressure difference. What is the answer for 28? So please go back and check, rewind the video and check. Right? Otherwise, if there's any other one who mark the answer, put it to the chat, right? So feel free to help each other, right? And it should be, that is how it should be. Okay, G, since that is coming from a pressure difference, right? G is coming from a pressure difference, no, H rho G. That is not gravitational acceleration, that is resultant acceleration. G here is resultant acceleration. We discussed in hydrostatics, that is resultant acceleration. Then you have to put resultant acceleration there. right? Resultant acceleration, isn't it? Right? Now, if this is moving downwards with 5, see what's happening. Now, since the setup is at Earth, right? Since the setup is at Earth, G acts downwards anyway. G acts downwards, right? G acts downwards. Now, when this setup moves downwards again by 5, right? We know for this system, the accelerations affect in the opposite direction, no? Accelerations affect in the opposite direction. If the bus moves forward, right, you will be moving towards backward direction if you are inside the bus. Something like that, right? When a car is moving forward, right, we are moving towards the backward direction, right? Then when this travels by 5, this liquid gets the acceleration to opposite direction 5, opposite 5. Right, now we can apply this equation again. You have to find h, no? Then h rho g equals, right? G එක තමයි substitute කරන්න ඕනේ. හරියට දාන්න ඕනේ දැන්. What's the resultant now? G minus 5. Then h rho, this is G minus 5 equals 2d over r. Then h rho G minus 5 is 5, no? 5 equals 2d over r. For 2d over r, we can plug from here, no? That is 8 rho g. That is 8 rho g, right? 8 rho g. 8 rho g. Now 5 and g can be cancelled. See? Then rho 2, rho cancels. G is 10, no? Then this is 5 times 2. See what's coming? H equals 8 times 2, 16 millimeters. Right? So 1 is 16. 1 is 16 millimeters. Right? There are 2 answers, sorry, 3 answers with 16. Then we have to check the other value as well. Right? To check the other value, let's do something like this. We can do the same. Right? Since the space is not enough, give me 1 second. Okay, visible, right? Okay, see, then do the same again. Now, if it's free fall means now it falls under gravity. When it falls under gravity, there will be, let me use a different color, there will be the opposite acceleration acting on the liquid again like this, right? Opposite acceleration acts on the liquid like this when it falls under gravity, right? Then if you apply this again, h rho, this is going to be G minus G, right? G minus G equals 2d over r, right? Then subject h, right? Then h is going to be 2t over r rho, and g minus g is 0. Now you are getting a 0 here. Anything over 0 is what? Infinity. Anything over 0 is infinity. Then what's the idea? H goes to infinity. Right? But total length of the tube is only 40 meters. Total length of the tube is only 40 millimeters. 40 millimeters. Then, since it goes up to infinity, then liquid level of the tube should be 40. Right? After 40, it will spill out. After 40, it spills out. Right? Nothing. Theoretically, it is supposed to go up to infinity. Then it should be 16 and 40. Answer 5. 16 and 40. Right? See, another application of capillary rise. So, we need to get the answer for 28 yet. For 28, we have marked 3. Okay. So, this is a YouTube live, no? Go back and check. It is 3. 31. Water rises to a height of 2 centimeters. In a long vertical capillary tube. If the tube is inclined such that it makes an angle 60 degrees with the vertical, what is the length of the water column along the tube? Right. Water rises to a height of 2 centimeters in a vertical capillary tube. Right. Now, in this scenario, it rises up to 2 centimeters. Then we know capillary rise is h rho g equals 2t over r, no? Then in this case, that is 2 centimeters. Rho g equals 2T over R. Let's keep this as equation 1. And our second scenario is, this is inclined, right? This tube is inclined. The tube is inclined like this. And the incline 60 to horizontal. Vertical, 60 to vertical. Yeah, 60 with vertical. Something like this, no? Something like this. What is the length of the water column? Okay. Then, see, we know, then liquid surface should be somewhere here. And let's say it is like this. Right, what we have in the capillary-Rice equation is this vertical height. Right, vertical height. Now, if we assume this as L, let's assume this as L. Using these triangles, we can get this. This should be L cos theta now. L cos 60 now. Right, we have a triangle here. With a triangle like this. This is L and this side is 60. Then this is L cos 60, L cos 60, and this is L sin 60. So we are interested about this L cos 60. Right? We are interested about L cos 60. Right. Then let's apply capillary-Rice again. Because H in capillary-Rice is vertical height. Right? H in capillary-Rice is vertical height. Then vertical height here is only L cos 60. Then L cos 60. Right? Rho G equals 2T over R. Same tube, then same R. Right? Same tube and same R. L cos 60 rho G equals 2T over R. Then from the first equation for 2T over R, we can plug 2 rho G, no? L cos 60 is half rho G. Right? 2T over R, for 2T over R, we can write 2 rho G. Rho G to rho G cancels. Then it says L equals 4 centimeters there. Right? L equals 4. Right? L equals 4. I explain 30th. Apply the equation of capillary-Rice. And where G is resultant acceleration. G is resultant acceleration. That is coming from hydrostatics. Because H rho G is coming from hydrostatics. Right? So we have proved that in hydrostatics that G in H rho G is not the gravitational acceleration. That is resultant acceleration. Right? Then you have to apply resultant acceleration accordingly as phi and 0. And simplify. So this goes up to infinity. Since maximum height of the tube is 40, then the height that we will see is 40 millimeters. Right? Even though it goes up to infinity. 32. Right. The bottom of a cylindrical container of cross-sectional area A has a small circular hole of radius R, as shown in the figure. When a liquid of surface tension T is poured into the container up to a certain height, the liquid just begins to seep through the hole. Right. Something similar to the previous beaker question we did. Right. Like this. Now at this point, this starts seeping through. At this point, this starts seeping through. We know, right? There should be a liquid meniscus here if this is filled with the liquid. Now, in this case, inside this filled. Inside it is filled with the liquid. Then if there is not going out, spilling out, seeping out, which means this meniscus is doing the thing. Meniscus is doing the thing. Right. Liquid just begins to rise. The liquid is then filled only up to half of that critical height. All right. So let's find this height. Since this is P naught, we can write an equation again. This is also P naught, atmospheric pressure. Right, either sides. Either sides we have atmospheric pressures P naught. Now if you start from here, P naught plus H rho G. And here we are jumping out from this minus 2D over R. Again in the atmosphere, P naught to P naught cancels. Then H rho G equals 2D over R. Right. So we got something like this. H rho G equals 2D over R. Keep this aside. And in the second instance, only half is filled. Right. Only half of this height is filled. Which means this should be H over 2. H over 2. Right. That's the thing, no? H over 2. Then, what is the minimum mass of the object required to cause the liquid to start seeping through the hole, right? So we know if this liquid is filled up to a height h, if this liquid is filled up to height h, it was just seeping through. If this liquid was filled up to height h, it was just seeping through. Now, by keeping a mass on this, if this can be immersed to this level again, if this can be immersed to, right? If this can be immersed to this level again like this, if this can be immersed to this level again like this, again it is going to seep, no? Right? It will start seeping. Again it is going to seep it if this same height is achieved. Then if there is a change in upthrust, right? Use delta U equations. We discussed all the equations in the class, right? Use delta U equations if there's a change in upthrust. Now, if the upthrust is changed to this volume, right? This additional volume of the liquid, again it starts seeping. That's the logic, right? Then, by keeping a mass, no? Apply delta equations. Delta U equals delta mg. Right? Delta U, additional upthrust. Additional upthrust is due to this part, additional part. Right? We know delta U equals delta V rho G. Delta V rho G equals delta mg. Then M2 sorry, G to G cancels. Delta V is A times H over 2. Delta. This is the delta part. This is a change. Right? Then A times H over 2. Right? And what about rho? Rho will cancel. Right? Keep rho. And this is our delta M. For H we have an answer. No? For H. Right. For H we have an answer. Right? For that we can substitute. Then let's do this way. H rho volt में substitute करो. Now this is A over 2. For H rho, from here we can plug 2T over Rg. 2T over Rg equals delta M. Then see these two cancels. This is a little bit different question. 2 to 2 cancels. Then what remains? Then it says delta M equals AT over Rg. AT over Rg. Answer 2. See? Another different one. A little bit different one. And it is linked with the idea of upthrust. Right? If there is a changing upthrust, apply delta U equations. If upthrust is changed up to this level, if the liquid filled up to this level by changing upthrust, again it starts seeping. That's the logic I used, right? Now to this side, the meniscus is like this to the other side, right? Changing part. For that changing part, apply delta U equations. Right. That's all. 32. Right. So which means with that, I have discussed 32 past paper MCQs from surface tension in the SY discussion, right? So get the benefit since we have covered all theory parts, right? All the theory is basically properties of matter is covered, no? Since properties of matter is covered, I'll be taking coming up SY discussions also for the question discussions of other covered up parts like viscosity, elasticity, and so on, thermal parts. And this week, since we are starting matter and radiation, now once matter and radiation is completed, finish. No, let me stop the sharing. Right. Then when we start, after we starting matter and radiation next week, right? To cover up matter and radiation questions also, I'll be allocating some SUA sessions, right? To cover up the matter and radiation and all other lessons coming up, right? Then you can get all updates through the channels. And once the theory part is covered, you can find all past paper questions at the back of the Tute as well, right? So from there also you can get these past paper questions and try them before I do the discussion, right? So if you didn't have the past paper questions, what you can do is you can download past paper questions from my Telegram channels like this, as we did today, right? As we did today, you can download all these past paper questions that is relevant to the ongoing discussion, right? That is relevant to the ongoing discussion. Before the discussion like this, right? Okay, then. So I haven't decided what are we going to take for the next discussion, right? Most probably it'll be something from center of gravity or thermal expansion, center of gravity or thermal expansion or viscosity, right? Let's see what's best. I mean, what's suiting best. So we'll take something, and as we cover the theory parts in the theory classes for other lessons also, right? In our regular class now, thermal is right about to finish, and after thermal we'll be starting gravitational fields, and in the reverse class, matter and radiation is ongoing, right? Ongoing in the sense tomorrow we are starting. So matter and radiation is starting. After matter and radiation, I'll be doing current electricity in reverse class. So likewise, when we cover these theory parts in the classes one by one, I'll be allocating SV discussions accordingly to discuss those questions, right? So get all updates through channels, and you can join these discussions and get the advantage, right? So it seems no any more questions. If there's anything before wrapping up, you can ask and get it clarified. Is it all clear about these questions we discussed? So it's altogether 32 past paper MCQs from surface tension. All past paper MCQs we have finished discussing. Right. All good, right? So again, reminding, we are 24 weeks ahead of your exam, right? Just 24 weeks. So spend this time effectively and productively. You have some kind of a vacation these days because of O levels also, right? Spend your time effectively and productively, right? So that's it. Then practice these questions again and again, and check whether you are comfortable with these questions to do by your own. Okay, then see you in the next S2A discussion of the class, right? Good night and goodbye. See you.